do image analysis in Python with SciPy and Scikit image. So I'm Juan Nunez Iglesias, this is Tony Yu, and we both developed for the Scikit image package. So yeah, hopefully if you know about Numpy but haven't done image analysis before, after this tutorial you'll be able to do quite a bit with image analysis. So that's just the intro, prerequisites. Yeah, if you've cloned the repository, you've got everything you need, the example images and the notebooks. So we'll start with the first. If you scroll down to sections, this link should just work if you're on IPython 2.x, which you should be. And so we'll open the first section, which is images and Numpy arrays. So the first thing you want to do is run map.lib inline, just so everything displays nicely in the notebook. Okay, and so in this first cell, all we're doing is making, using numpy.random to make a matrix of 500 random numbers. I think they're between 0 and 1. And importing pyplot and CM, which is the color maps submodule. And then we just want to do imshow, show the image of the random matrix that we just created using the gray color map. And Tony will talk more about color maps in the next section. And using nearest interpolation, which is basically saying no interpolation. Okay, so if we run that, this is what we get. It's just black and white splotches. There's gray levels in there, so that's what you would expect. So again, you're going from a NumPy matrix, and you're just treating that as an image. That's all it is. Okay, so in Scikit image, which is addressed with the name skimage when you've installed it, has a data module with just some example images. So we're just going to load up the coins image, and we're going to look at the type, its dtype, its shape, and show it. Again, the call to imshow is the same as before. Okay, so coins, our example data is just a NumPy array. There's nothing else associated with it. It has type uint8, so unsigned integer 8-bit, and that's the shape of it. And so this is the image here. Why don't we just add, if we go below, let's plot the min and the max. So, wait. Oh, sorry. That's weird. Yeah, I'll just do full screen. Right. Okay, so this is what I was typing. Just made a new cell, coins.min, coins.max, and that's what they are. Any uint8 image is going to range from 0 to 255 maximum, so this one doesn't use quite the full range. Yes. Better? Thanks. Okay. Then we're going to try a color image. So Lena is a very common example in computer vision applications. So we ship it with Scikit image. And here, because it's a color image already, we don't need a color map. So a color map, all it does is it takes intensity values and maps them to some set of colors. Here we already have the colors, so you don't need a color map. So we just have imshow with the interpolation. And that's the shape of the image. It's 512 by 512 by 3. So the 3 at the end is just the 3 channels, red, green, and blue. And these are just the 2 spatial dimensions. So again, it's just a NumPy array, but it has an extra dimension in addition to the 2 spatial dimensions. And so because it's just a NumPy array, we can do very simple things just with slicing, such as making a square that's completely red. So we're just going to take every pixel between 100 and 200, 100 and 200, and this is again the channels, and we're just going to make that equals to 25500. So that's red, green, blue, so it's going to be red. So if we do that, you'll see that there's a red square there. Okay? So pretty simple. Is everyone with me? Yeah. Okay, so we come to the first exercise. It's a little bit of NumPy indexing. That's all it is. If you're familiar with NumPy, you should not have too much trouble. So all you want to do is draw an age, which is just, a set of, it's specified here, 24 pixels this way, 20 pixels this way, 24 pixels this way, and each of those has to have a width 3. And so the input is an image, the coordinates of the top left of the H, and whether you want to modify the input image or get a copy. So there are the 3 parameters. So have a hand at that, unless you think it's beneath you. But it should be pretty easy to do, and then you'll just, once you've got it, try it out here and make sure that the H displays how it should. And if you have any questions about this, raise your hand. We'll come around, help you out. I'm just not sure I want to do this live. Let's go for it. No, I don't. Almost there. Yeah. Okay. Hopefully that works now. What just happened? All right. Okay, has everyone got that? Has anyone had any issues with this? No. Sorry? Yeah. So here's my solution. So just define green for convenience. This is the row and column of the Numpy array where we want to have the top end, height, the width, and the thickness, just specified over here. If we don't want to modify the image in place, then we do image.copy. And then, yeah, basically you're indexing from row to row plus height and column to column plus thickness, and you're making that green, so that's making the left bar. Same thing here, but you're going from column plus width minus thickness to column plus width. And then you do the strut, which is horizontal. So you have these thick rows from there to there, and you make that green. Okay, so pretty simple, I hope, and you can see the H drawn there. So again, you can do anything you can do with Numpy arrays, you can do with images in this environment of SciPy and Scikit image. Did anyone get to the next bit? I mean, this is essentially, it's pretty simple. You just do plt.plot of, oh, no, right. So if you have a color image, it's a bit more complicated. So let's just do if image.endim is less than 3. So can anyone tell me what I'm doing here? Sorry? Yeah, so this is saying if the image is grayscale. And what I'm going to do is just add a dimension to it at the end, just so that the code that I do later works. Image equals image of ... comma. Okay, so this is giving me a channels access for a black and white image. And then I can just do for channel in, and then we're going to do image of ... comma I, or I in range image dot shape of -1. Okay, so this is saying for every element in the number of dimensions, which is the last item of the shape, give me that image. And then I'm just going to do plt dot plot ch of row. Okay, so hopefully this is going to work. Oh, I forgot. So you probably want to do a new figure. So let's try that again. F equals plt dot figure. All right. Yep. So this is the black and white. This is the coin. So you can see they're going black, and then there's a coin, so the intensity goes up a bit. then black again, then coin. And this is Lena, this is the RGB spectrum. Okay, so.
All right, so it's going to take me a second to compile. I'm going to use slides, actually, as opposed to the raw IPython notebooks. But you'll actually be following along in the exact same thing I'm using to build my slides. So if you go to the index and look at the second listing, which is color and exposure, then that's the notebook that we're going to be using. Click on it. It should be uncompiled, but the version that I have is compiled. I got a bit of an error, actually. Sorry. Oh. All right, I already have the server open. Sorry about that. All right, so like I said, I'm going to be using slides. I'm going to jump back and forth to the notebook, color and exposure. Everyone have this open now? Know where to find it. Okay, so I'm going to be repeating a little bit of what Juan started off with in this part of the talk. So first off, I want to do a little aside about plotting images. So we've already seen that we can import images, sample images, from Scikit images data module. So most everything in Scikit image is divided up into modules that you use for specific tasks. So we have a data module that has sample data. So we're going to import an image from there, the cameraman. And we're going to do pretty much the standard IPython plotting imports. So we want to plot matplotlib inline so that figures are actually in the notebook. We're going to import matplotlib.pyplot as PLT. And Numpy as NP. So these are just the standard aliases that we're going to use. All right, so one thing about plotting images in matplotlib, the default is this color map called Jet, which is a terrible, terrible default. If you look at this image, it's somewhat pretty, but it's really bad for grayscale images because it distorts your data. So if you look at this picture, so I'm just zooming into the cameraman's face, and you look at this area on the cheek and the forehead and the nose, and it looks like it's very distinct from everything else. But if you look at the grayscale image, it's just part of the face as you would normally expect it. There's nothing special about it. There's no beauty mark on this guy's upper lip, which there's a red spot right here if you're looking on your own notebook. It's not there, and it's only there because of this kind of banded color scheme of Jet. So we're going to actually set the default color map to grayscale, and we're going to set interpolation equals to none. This just avoids issues with confusing pixel boundaries with non-pixel boundaries. So the default will smooth over pixel boundaries, but for the purpose of this tutorial, it's nice to actually know where they are. Okay, so just to review, color images have a third dimension. So here is a picture of a cat. It's in color, and by color, we mean we have an array that is 3 dimensions. So it has a height, so a height of about 300, width about 451, so these are the first 2 dimensions, and the last dimension is just the RGB color channels. All right, yeah? So from the top left, right. So if you're used to matrix libraries, that's typically what they do. Drawing typically, I'll say near the mic. Drawing typically has the origin at the bottom left, but arrays, NumPy arrays typically have, or matrices, for example, if you were to index II into a matrix, it would be the top left corner. So yeah, so most of the graphics processing libraries that you look at are going to have the origin at the bottom left, and they're also going to give you width by height as opposed to height by width. But NumPy arrays are number of rows by number of columns, so height by width. So this is a little confusing, especially if you're used to graphics libraries or image processing libraries that have nothing to do with array processing. All right, and then the last dimension is just our red, green, and blue color channels. So just some basic array manipulation. If I want to use some slicing and indexing to grab the red color channel, we would do this, right? So we're just taking all the rows, all the columns, and the 0th channel, so the red channel. It's in red, green, and blue order. So this should give me the red channel. If I plot it, I get this gray picture of the cat. Everyone should be clear that this slice that I did just gave me a 2D image. So a 2D image, like we said earlier, is just a grayscale image. So this shouldn't be too surprising. We're going to do a quick exercise just to make sure everyone's on the same page. I want you to create 3 different images and plot them so that the red channel shows up green in a plot. Or sorry, the red channel shows up red in the plot, the green channel shows up green, and the blue channel shows up blue. So there's a little bit of, there's a little sort of helper module that we developed for the tutorial called skdemo. Scroll down. And if you look in skdemo, there's just a couple of little helper functions. So I'm going to say skdemo.iamShow tab, and you'll see that there's an iamShowAll and an iamShow with histogram that we're going to be using just to simplify some of the plotting that we're doing. You can do all this plotting. So let me just show the next code sample. So basically, I'm using iamShowAll to show 3 different images by passing those 3 different images to it. We can do the exact same thing if I scroll back up here using matplotlib's subplots command. But since we're just plotting images, we're just going to make a really easy helper function so we don't make the code too noisy. So I've gotten you started off with 3 arrays, the red image, the green image, and blue image that you need to fill out with some slicing. All right, so hopefully you guys are most of the way there. If not, I'm just going to run through a quick example. Okay, can everyone see the text on my screen? Just bump it up there. Okay, so we just need to slice into, so I just filled out this array with an image that was filled with the zeros of the exact same shape and data type of the color image. So it'll be as close as possible to the color image, but with no actual information. And that's why showing it up is all black. It's just zeros, so it's going to show up black. So I'm just going to take my red image, and I just want to fill it with my red channel, or just fill the red channel of the red image. So that would look like colon, colon, so all rows, all columns, and the 0th channel. And I fill it with just the red channel of the image. Oops. So I run that, and I get my red image. You can go ahead and copy and paste that for the blue image as well. I'll just do 1 and 1. Oh, sorry. Oh, wait. Oh, green is, yeah, green, RGB. Yes. Okay. So you get the idea. Pretty simple, hopefully. We won't be doing that much slicing in this tutorial, I don't think. So if you're not that comfortable with NumPy, I think it's okay. All right, so moving on. Any questions, actually, before I move on? Okay. So moving on, like Juan just showed you, you can combine slicing in the channel dimension with slicing in the rows and columns. So this, again, is just the first 100 rows, the first 100 columns. And I'm going to set channels 1 and 2, so green and blue, to 0. And similarly, I can look at the last 100 rows, last 100 columns, set channels 0 and 2, so red and blue, to 0. So that just leaves this green square. Okay? Everyone comfortable with that? All right, so that's all I'm saying about color now. We're going to revisit it a little later on in the talk. So histograms. So histograms are a great way to get a quick measure of the exposure of your image, which is what this section's all about. So if you're in Matplotlib, you might want to plot a histogram like this. So you might use the hist function, say plt hist of the color image, right? That seems like a pretty obvious thing to do. If I run that, then it gives me this nasty looking trace pack, and it says value error x must be 1D or 2D. Anyone know why? Yeah, so I have a 3D image. Matplotlib actually does something special with 2D things that we don't want it to do. It tries to plot multiple histograms. So 2D even wouldn't be valid. A 2D image wouldn't be valid either. It would do something, but it wouldn't do the right thing. So I think I heard someone mention what the solution is. How do you take this image? I'm sorry? Reshape it. So how do you turn it into a 1D array? The easiest way. Flatten, yeah. So dot flatten on our array will give us a histogram that looks like this. We might want to do a little bit more to this to make it prettier, to make it maybe a bit more accurate with our color image. And that's actually the next quick exercise. So we're going to plot a histogram for each color channel in the image, all in a single plot. And if you have time, maybe play around with using just the plot command, not the hist command, along with fill between, or fill between, along with the histogram function from Scikit image, Scikit image.exposure in this case. All right, so if you're chugging along, keep working. I'm just going to give a quick hint. Or maybe not even a hint, just a way to make things a little easier. So ideally, I would iterate over the channels of my image. That would be really nice to do. One way to do this is to use a command called roll axis in Numpy. So let me just back up a second. So my color image has a shape of 300, so the height, the width, and then the number of channels. If you iterate over that array, it's going to iterate over the first dimension, which is the rows, right? So ideally, I would want to move that last dimension to the front and iterate over that. So one easy way to do that is using np.roll axis. And you just specify the axis that you want to roll to the front. And I'm going to say -1. So -1 is our last row. Move it to the front. I'm going to just print the shape. And now I have 3 at the very front. So this is going to be my color channel that I'm iterating over. So if I put that in a for loop, then for channel in roll axis color image, just might as well print the shape of each of these channels. And you can see I get my images back. So this is first the red, and then the green, and then the blue channel images. All right, so hopefully you got as far as calling PLT hist on each of these channels. Again, we have to flatten it. And you get 3 histograms that might look like this. I'm surprised that it's actually red, green, and blue. They're in the wrong order. Oh, yeah, they are in the wrong order. OK, good point. This is just fortuitous that the first 3 colors in the, well, maybe not fortuitous. That the first 3 colors are red, green, and blue, but they're not in red, green, and blue order. So you might also want to iterate over some sort of color spec. So I'm going to zip this iteration up with RGB. So matplotlib recognizes that red, green, and blue are red, or RG or B. And I'm just going to pass this along to the color argument of plt.hist. And now they're in the right order. It's a little hard to see, so I'm going to just tweak it with a little bit of alpha value, so just transparency, or I guess opacity. So I'm going to lower that to 0.3. So now you can actually see kind of the structure. Yeah. Oh, sorry. So this is iterating over 2 different things. And so the first element of the first thing, I'm going to take with the first element of the second thing, and that's passed along to my iteration. So I have color and channel. So it takes RGB, so the first time around takes R, just the letter R, and then the channel, and it packs them together, pushes them to the iteration. Right. All right, so this is OK. You might want to play around with the number of bins, so it's a little higher resolution. The bonus was to actually not even use the hist function and plot some lines instead. So instead of using the hist function, we're going to, actually let me open up a new cell, say from skimage import exposure. And exposure, oops, yeah. Exposure has this function called histogram. This was pointed to in the notes. And if you look, it just says, give me an image. The nice thing about it is that you don't need the number of bins. Can I pull this up? Yeah, you don't actually need to pass it a number of bins. For integer arrays, it's just going to default to the integer values of your array. For floating point values, however, it's going to use the number of bins here. And that's usually what you want for images, especially.
Yeah, so you might want to point out the other histogram, you're getting artifacts because of the beginning.
Oh, exactly. So what Juan just said is that you're getting these artifacts. And I think I talk about it a little bit in the notebook. I don't have slides of it. But you're getting rebinning because you have integer values at very specific places, and you want a certain number of bins. If your total number or range of intensity values doesn't divide evenly into that number, that range of intensity, then you're going to have two intensity values in one bin and then 3 in another, just because you can't evenly divide them up. So you get these weird little spikes, right, because you have more intensity values in those bins. OK, so we're going to use the histogram function. And this is going to return, oh, let me actually look at the doc string again. It says it returns the hist, so the counts of the number of pixels at a given intensity, and the bin centers, so what integer values our histograms, those histograms correspond to. So we take our color image. Actually, I don't want to do this in here. I want to do this in the loop. So I'm going to destroy this little example that I put together. So instead of calling hist, I'm going to take exposure.histogram of my channel image. And I'm going to get back the hist, so the counts. Maybe we'll call it counts. And the bin centers. And this is my, so counts is actually the y in the histogram, right? So this is the count of the number of pixels, and these are the intensity values. So we're going to flip these arguments when we pass it to plot. So bin centers, actually let's get rid of all, let's keep color. So bin centers is my x value, and counts is my y value, right? So that doesn't look that clear. Oh, yeah, that's right. I do not need alpha anymore. Right. So now I have my red, green, and blue color channels. There's no artifacts from binning your integers, which is great. You can also use fill between, which I think is pretty. And pretty counts for a lot. Fill between x, maybe? Oh, no, not x. Fill between. And in this case, we want alpha, so that we can actually see all 3 curves. All right, I just wanted to go through that because we're going to use this image with histogram function from this little plot utilities module. And I don't want this to be a mystery how to do this stuff. Okay, any questions before we move on? So there's no solutions in the notebooks themselves, but I'll be posting them afterwards. I want to make you actually do the exercises or try to do the exercises, just to force you to think about it a little bit. But I will be posting those after the tutorial. All right, so that was just a kind of a how to plot histograms. What are histograms actually in terms of images? So like I said earlier, we're going to use image with histogram. This function just basically does what we did for that exercise. So this removes all that boilerplate that we had there. Yes? It's just a 1D array. So it's just the centers. So like for integer values, it was just 1, 2, 3, 4. Yeah. OK, so we're going to use our function imAmShow with histogram to plot the cameraman image that we saw earlier. So the nice thing about this function is it also plots the image right next to the histogram, and you don't have to fiddle with any sort of configuration. So this histogram shows you a couple of interesting things. So we have this man over here in this image with a very dark coat, dark hair. So we have a lot of really dark pixels in a very tightly bound region. So we have this spike in the low intensity region. So intensities go from low to high, and that's dark to white, so black to white, or dark to light. So this spike right here, if you look at my mouse, this spike corresponds to all these dark pixels that are in the man's coat and his hair and the tripod. Right? And then we notice that we have a spike in the middle, in the kind of the gray region of the image. And that makes sense because this image itself looks fairly gray. All right, so that's the basic histogram. The values you'll notice are the intensity, and that's just the pixel intensity. And they go from 0 to about 250, let's say. Right? And the reason they go from 0 to almost 250, or well, just above 250, is because the image data type is uint8, so unsigned 8-bit integer. So this is a really, if you don't do images very often, you probably don't come across unsigned 8-bit integers that much. They're actually really popular with images because you get to store a lot of data somewhat efficiently, right? Whereas if you're using float64 or double, then you're using 8 times as much space. So you'll see this a lot. uint8 causes problems. We're going to see that later. Remember this hint? We'll come back to it. Okay, so like I said, the uint8, if we look at the integer info, so this is NumPy's integer info function, you can figure out that the min and the max are 0 to 255, or you might have known that already. Okay, so now let's look at a color image. So this is the cat from earlier. I'm going to just plot another color image for, plot another color image for comparison. So this is Lena, which Juan showed you earlier, and another histogram. So you'll notice that the histograms look really different. So the top histogram has maybe a somewhat Gaussian-like quality, or each channel does at least, and they're shifted. Whereas the other one has a lot more structure. The one on the bottom has a lot more structure to it. Any guesses as to why it might look so different? I'm not sure if it's been processed. Okay, yeah.
There may be some natural color filtering.
Yeah, that definitely might have distorted the image. But just looking at this image, is there anything you can tell about it that might make? Yeah, so it's mostly red and blue. It's actually very flat in color. So we have, the background here, the wall here in the background is fairly uniform in color. The hat is fairly uniform in color. I mean, there's some shadows and some gradation, but it's fairly uniform, and it has very sharp edges in this image between these distinct regions. So you have these sort of separate peaks for all those different regions and textures or uniform areas of your image. Whereas this cat is pretty much, there are some distinct regions like the eyes, but for the most part, there's subtle color variations with very few sharp edges. So I want to point out that I'm doing this analysis on color histogram images, histograms of color images, but really histograms of color or RGB images is kind of useless. It's pretty, that's why I plotted it. But really, like if you have a pixel that has a lot of red value and no green or blue, then it's red. But if you have a high red pixel with a little bit of green, then it's yellow. And that doesn't at all, that shouldn't be binned together in the histogram that I want to look at. But there's no correlation between the binning here in the red histogram and the binning here in these other two histograms. So it's not that useful in practice. We'll talk a little bit about color spaces, where we transform color images, and that'll be a little more useful. Okay. All right, so histograms and contrast. So the whole point of this section is to talk about exposure. So if you have a low exposure image, then you have low contrast. So you can actually use histograms to figure out how to increase the contrast of your image. So here again is our cameraman and the histogram. And if you look at this histogram, you can see that there's this region. So remember, this intensity value should go up to 255 because it's a uint 8. But there's nothing between, let's say, 180 and 255. It's fairly low. You're not using those values. And you can see that in the image. There's not very many white pixels there. So this is what you might call low contrast. It's a little dim. So just by looking at this histogram, you can figure out good bounds to stretch your image. So one way to increase that intensity is to take some value, like 10 at the bottom end, and stretch it to 0. And at the high end, I'm going to take an intensity value of 180 and stretch it to 255. So I'm going to make 10 black, an intensity value of 10 black, an intensity value of 180 white, and everything in between I'm going to linearly interpolate. And that's what this rescale intensity function does. It basically just linearly interpolates between the two bounds that you've set. So you can see here that we actually have a lot of pixels now that are white. You can't see it because it's kind of touching the edge of this plot, but there's a lot more pixels that are black. And we've stretched everything in between. Right? And of course, the image, you can actually see a little more white in the image. Is everyone clear on what that's actually doing there? Cool. All right, so linearly stretching your intensity values is basically the simplest thing you can do to enhance the contrast of an image. One of the classic techniques for doing it that's a little more sophisticated is called histogram equalization. So here again is our image of the man and the plot of the histogram. And I've also plotted the cumulative distribution function in red. So that's this curve here. If you look at the Y label on your screens, not on mine, then it says the fraction of pixels below the given intensity. So if I'm at a particular point, let's say 10, then about 20% of the pixels are at or below that intensity. So this is just like how a lot of people report test scores, so percentiles. If you're in the 90th percentile, then you did as well or better than 90% of the people. So that's all this is saying. The reason I plot it here is because one measure of contrast is how well you're distributing your pixel intensities. So if you had a perfectly uniform distribution of pixel intensities, then you would be using your pixels to their maximum value in some sense. And that would give you a linear CDF, the cumulative distribution function. And histogram equalization is just that. It tries to maximize your usage of these pixel intensities. So earlier when we looked at contrast enhancement, we made the background more white and the man's coat darker. But you can think of the fact that this high peak here, all these black pixels that are in this man's coat kind of prevent us from resolving any details in the man's coat. So if I actually spread out the pixels that are all bunched together, then we're going to be able to resolve more detail in those regions where we're kind of wasting a lot of pixels. So if we look at the result, so there's an equalize hist function to do histogram equalization. If we look at the result, we do exactly what I just tried to describe, which is we take all those pixels that were bunched together and we spread them out. And consequently, we kind of push together some of the pixels that are less used. So this trough up here at the top, is kind of bunched together, and their bins are increased because we need to make space for those larger peaks. Okay. So one thing you'll notice is that the data type of the image changed. So now instead of a uint 8, it's float 64. You'll notice that the values go from 0 to 1 now. So Scikit image tries to ensure that it can take any data type of an image, but it doesn't guarantee that the output will be of the same data type. Sometimes this is just more efficient. You don't want to do conversions all the time to make sure you're in the same format. Sometimes some data types can cause problems, which we'll talk about later. If you really, really need to guarantee that you have a specific data type, Scikit image has a series of functions under the parent namespace. So let me just. So if you say Scikit image or SK image, image as, and then tab, then you'll see that there are functions to ensure that you're working with a bool or floats or doubles, ints, uint, ubyte, etc. Okay. So if you really, really need to have a specific data type. Yes, exactly. Uint here is uint16. Okay. So this is just to kind of extend the idea that we had before. So histogram equalization is sort of a very classic technique. If you took an image processing course, then this is a technique that you would learn. There are also modifications that you'll find that are newer, that are better. They're available in Scikit image. I don't want to talk too much about it, but just know that there are other functions out there to use. So this solves some issues with normal histogram equalization by looking at local areas instead of looking at the global histogram for the entire image. It tries to look at patches of the image. Also, if you look back at the histogram equalized image, oops, it seems a little washed out in the background, whereas this contrast equalized, contrast adapted histogram equalized image looks a lot less washed out because it tries to limit the amount of contrast enhancement you get. So like I said, there's some more advanced functionality here. Excuse me. There's some more advanced functionality here. I said it was looking at local patches. You can, of course, control the size of those local patches. You can also control this contrast limiting with some control parameters, with some input parameters. So go ahead and look at that docstring after the tutorial. All right, so one more important aspect of image histograms is for thresholding. It's very useful for thresholding. So if you want to segment or divide an image into meaningful regions, so for example, you want to separate the background from the man, you will use what's called segmentation. And Juan's going to talk about that a little later this afternoon. But the very simplest form of segmentation is thresholding. So it's basically you pick a threshold value, you say that everything above it is background in this case, and everything below it is my foreground. So if you look at, so you can obviously just try random values and try and threshold, but that's not the way you should be doing it. You should at least plot the histogram and look for meaningful places to draw your threshold. So we've already analyzed this histogram to death. We know that the man and his coat are in this black spike here, and the background is in this sort of gray spike in the middle. So an obvious place to draw a threshold is right in between the two. So in this example, I'm picking 50 as my threshold, which cuts between these two peaks, kind of right in the trough. So that seems a pretty reasonable guess. If we use it, so here I'm saying, show me the images, so the pixels in my image that are greater than the threshold. So I'm going to paint those as white, all the pixels that are greater than the threshold, and all the pixels that are less than the threshold are going to be black. And so you can see that it does a pretty good job of segmenting the man from the background. Right? So as you might expect, there are some algorithms for automatically detecting thresholds. One of the most popular ones is called Otsu's method of threshold detection. So you just give it an image. It's all you do. There's no free parameters. It just figures out the optimal threshold. It does this by figuring out or by minimizing the variance within the two classes. So the variance on one side is minimized compared to the variance on the other side. The details aren't that important, but know that you can just throw an image at a function and get a good estimate for this image. It may or may not work for your particular image. So if we plot that, you can see it actually does a little better job of figuring out the threshold. So it gave us a threshold of 87. We guessed 50. And you can see that it resolves the pants on the man completely. Oh, sorry, this is a little low. I don't know why my screen isn't quite the same size as the projection screen. But the pants on the man are also captured with this thresholding parameter. All right, so before I move on to color spaces, let's take a break.